start by clearing out some backlog of stuff from the last couple days that was just not addressed at the end of class and then I moved on and didn't do. The first one is something that I really want to do because this is page 125. I said in class that one of the most important facts about trigonometry is the Pythagorean identity, which says that sine squared plus cosine squared is always 1. And the reason it's true is just because the unit circle has radius 1. But let's actually use that to do something. So here's the most obvious application of Pythagorean identity. If you know sine, then you almost know what cosine is. And if you know sine and cosine, then you know all the trig functions. So let's put this into action and see what we can get. So let's suppose I give you an angle, theta. I don't tell you what that angle is, but I tell you that it is in quadrant 2, and the sine of that angle is the square root of 5 divided by 30. I claim that that is enough information that you can tell me all of the trig functions at this angle. Let's try to do it. This is an application like Pythagoras' identity, right? So I guess we should probably use that. So maybe I'll start by writing out the Pythagorean identity, and we'll see what we see. So I want to find cosine theta first, I think. That's the most, I think, obvious choice. Pythagoras' identity says that sine squared of theta plus cosine squared of theta is always equal to 1 no matter what angle theta you plug into it. For this particular angle, do I know at least one of those two things? What does this problem tell you about theta? Well, I just don't have it in front of me. Does it tell you sine or does it tell you cosine? Sine. So I know what sine of theta is. We can replace this with what I know sine of theta to be equal to. And I don't want to have to keep writing cosine theta, so I'll replace cosine theta with c. So what does this equation become? This now becomes root 5 over 3. That's a terrible 5. Squared plus c squared equals 1. That look like an equation you can probably solve for c? Presumably. In fact, how many people just, while I was stalling, I already have done? Cool. Oh, I haven't yet. So I guess I'll give people a chance right now. I could do a talk through the algebra, but it looks like it's just like a quadratic equation, right? So you know how to solve it. Should I talk through solving that for c? Nice. Then I will wait a bit. You will figure out what c is equal to. You will compare with those around you. And then we'll come together. What do you think? Oh, cool. Does that negative affect the following answers? It looks like you've already done it. Okay. Yeah, cool. Let's hear it. What are we getting? I hear a square root of 2 over 3. Do I hear a second? Do I hear a disagreement? mean, I didn't do it just now, but I seem to remember a different answer being the one I remember coming up with. Do I hear a different answer? Yeah. I hear a negative 2 over 3. Should we go through it? Yeah. So let's do it. So I suspect I know exactly where something went wrong. It was somewhere in dealing with the square and the square root. But let's go through the walk. So to get C on its own, what seems like a good first step? Well, I can't take the square root. So you're saying like take the square root of the whole, everything on both sides? Yeah. Ooh, square root does not behave well when there's a sum underneath it. In that you can't like cancel those two squares with the square root. Instead, I'll propose getting C squared on its own and then square rooting. And maybe I'll do this first. Well, no, let's not. So I guess that means I want to subtract this to the other side. Getting C squared equals 1 minus root 5 over 3 quantity squared. That seems sensible enough? The thing that's added to C squared, just move that to the other side. The right-hand side of that equation, we should probably simplify that some though, right? How do you, so let's deal with back to that fraction, root 5 over 3 is squared. How do you square a fraction? Yeah, squaring behaves well with multiplication and division, right? Because squaring just means multiply it by itself, and fractions are easy to multiply. So you'll get, in the numerator, you'll get the square root of 5 squared, also known as 5, and divide by 3 squared, also known as 9. 1 minus 5 over 9. So far feel okay? All right. What is 1 minus 5 ninths? 4 ninths. So I'm out of space there, so go to the next line. C squared equals 4 over 9. And how do I now get C on its own? Do the square root. And I'm going to do something slightly wrong, and slightly wrong in a way that will affect the final answer. So C is going to be equal to the square root of 4 over 9. I do anything wrong here? It will simplify now to root 4 over root 9. And what's the square root of 4? Square root of 9? There's still something missing though.
Plus or minus.
Yeah, whenever you take a square root to undo a square, you lose whether the thing's positive or negative. And that really matters here. So, on the day when we did this, I talked about this fact that the Pythagorean identity, whenever you use it to find cosine, it won't know whether the answer should be positive or negative. You need to do something else to determine that. And I heard negative 2 thoughts. Why negative? Yeah, this angle's in quadrant 2. So, in order to figure out this plus or minus issue, let's focus on this quadrant 2, and maybe even draw a picture. I think I'll be okay with using space all the way down here. There's quadrant 2. And cosine is the x value that comes from rotated by that angle. So in quadrant 2, will cosine be positive or negative? Negative. All right, so we now know cosine theta. Cosine theta is negative 2 over 3. So when you rotate by this angle, you could even draw a picture down here. The y value appears to be root 5 over 3. Nope, the y value seems to be root 5 over 3. Whatever that decimal approximation is, I don't know. X value is negative 2 over 3. Cool. We feeling all right? Is this enough information to find the other trig functions? And maybe I'll see how people feel. Do people want me to talk through the walk needed to evaluate one of those four remaining functions? Cool. Which one do you want? Let's do secant. And then the others, I'll parcel you all up, and you'll do those computations separately. So secant. What is secant?
Reciprocal cosine.
Reciprocal cosine, right? It's 1 over the x value. Cosine is the x value. So secant theta is 1 over cosine theta. So that's 1 over, I know cosine, it's negative 2/3. 1 over negative 2 over 3. All right. And how many people, upon getting an answer like that, would want to just like stop and call it a day, put a box around it, and call it good? All right. I mean, it's not long, but like we do that on an exam, I'll like take a point up and say you should really simplify your fraction. That's division by a fraction, right? How do you divide by a fraction? Well, you said the one reciprocal, so like dividing by a fraction is the same as its reciprocal. 1 over a fraction is that fraction upside down. So that's 3 over negative 2. And what could I do with that negative in the denominator? Bring it to the front. All right, whenever you want to simplify a fraction, you want to like do everything you can to make the denominator as simple as possible. The cost will be the numerator might become more complicated. But that's okay because the numerator always behaves more simply than the denominator, right? Like when you add fractions, the denominator is what gets complicated, not the numerator. We feeling good? So, here's what I'd like you all to do. There are 3 remaining trig functions, so I'll split you up into roughly columns. Because if you're on an edge case, then you get to pick cosecant, cotangent, tangent. There are enough people that everyone should be sitting in some proximity to someone that they can talk to. They might have to turn around to do so. If you want to ask any questions, go ahead and I'll come around. We can talk about how to simplify that. Since it is like a decimal in there, we might even just like leave it because it's not a perfect square. So you can't do a whole lot to like pull it out. If you want to, you can rewrite that as a fraction and see if it's made a perfect square back ours. Which we can talk about exactly that one in just a moment. Because I think it won't simplify a whole lot, but it simplifies some. Cool. In fact, let's come together. So cosecant, what you get? I guess either a decimal value or an exact value. I'll be happy with either for now. I like that. 3 root 5 over 5. How many people instead wrote down 3 divided by root 5? Oh, cool. Yeah, those are in fact the same. This one's the more simplified one. Is there a copy to talk through that one? Nice. Cotangent. Ah, okay. One more time, or should we talk through it? Oh yeah, let's talk through it. So what gives you cosine? Sorry, cotangent. What formula gives you cotangent? Yeah, because it should be x value divided by y value. That's cosine theta divided by sine theta. And you know what cosine is? It's negative 2 over 3 divided by sine is root 5 over 3. And, well, I don't know, how many people got there and then just stopped and called it done? Good. It's not simplified yet. I see a fraction in the denominator. How do you divide by a fraction? Multiply by the reciprocal. So this is, go to the next line because I think I'm going to be shy on space if I keep going left. Negative 2 over 3, the numerator stays the same. Multiplied by the reciprocal of the bottom. 3 over root 5. Alright. That's better anyway in that there aren't fractions in the denominator anymore. Do you see anything that simplifies right now? There's some 3's in common, right? Let's cancel those. And in fact, we could have just canceled the 3's at that step, right? If you divide the numerator by 3 and divide the denominator by 3, those divides cancel. So we could have canceled one step sooner. So it looks like I get negative 2 divided by root 5. So that's a simpler answer than we started with anyway, right? It's fewer characters. But I still see a square root in the denominator. I don't like to see a square root in the denominator. I would rather see a square root in the numerator. So what could I do to get that square root not to be in the denominator anymore? Yeah, I wouldn't want to square it because that would change what the fraction is. I need to do something that will make it continue to be the same number, just a simpler looking form. And one thing you can always do to a fraction is you can multiply and divide by a single number. As long as it's the same number, it doesn't change the fraction. I'm going to pick the number that will make the denominator look nicer. Multiply by root 5 over root 5. Because, what's the square root of 5 multiplied by the square root of 5? 5. Square root of a thing times square root of the same thing is the square root of thing squared. Oh, square root undoes square. Nice. Cool. How about that last one? Tangent theta. What do we get?
Square root 5 over negative 2.
Want to hear root 5 over negative 2? Do I hear agreement? Yeah. So that'll be y over x. And I guess that one was easier in that, like, that's what you started with. But you can cancel the divide by 3's. Yeah. So here's the payoff. If I tell you what one trig function is, and I give you enough information to figure out what quadrant the angle lives in, then you know all the trig functions. Yeah.
Cotangent should be negative.
I agree. Or did I lose the negative sign at like the very first step or at the end?
At the end.
Yeah, okay. Oh no, I didn't lose it. I just wrote illegibly. Groovy. This example feel pretty alright then? And there will be at least a few web walks in which I'll have you do this. This example will come up later on in the class again when we talk about inbox trig functions. Next one I want to do is more like wrapping up stuff that we just didn't do in the previous lecture. So, what happened last time? I promised you that we'd go through and evaluate things on the unit circle. And we dealt with what happens at an angle of pi over 4. But there are two more angles in that unit circle that we haven't addressed. I want to use right triangle trigonometry to now address that. So to do so, let's see what we can do. Let's try to understand trig functions at pi over 6. And I'm going to use the SOHCAHTOA philosophy, right triangle trigonometry, to figure out trig functions at pi over 6. So here's what I'm going to do. I'm going to draw a trig function. I'm going to draw a triangle. I'm going to label an angle as pi over 6. I'm going to assign, if you want the page number, that would probably be helpful. 129 is where I am now. If you want trig functions at pi over 6, draw a right triangle with that as one of the angles. So you have a right angle here, that's why that's a pi over 2. I will assign the hypotenuse to be length 1, just in order to make some steps later on easier. I will label the opposite side as B, the adjacent side as A. This so far should look an awful lot like what we did for pi over 4, right? So now I just need to do something with that triangle to figure out what's going on. The first thing we did when we walked with pi over 4 is we found that unknown angle. We have enough information that you could solve for that angle alpha? Yeah, you do. It's a matter of whether I should do it or I should be quiet and have you do it. Should I go through the work to find that alpha? Cool, then I will. What do angles inside of a triangle have to add up to? In degrees or radians? 180 degrees. Angles inside a triangle add up to 180 degrees. So this angle plus that angle should add up to 180 degrees. Angles sum to 180 degrees. But everything in this diagram is in radians. So let's put that 180 degrees in radians. How many radians is 180 degrees? Pi. If you wanted to walk in gradients, this other weirdo measure that I mentioned only briefly and said I wouldn't again, I guess angles add up to 200 gradients. But don't care about that. Equals pi radians. So that means that this angle, pi over 6, plus that angle, pi over 2, plus this unknown angle alpha, has to add up to pi. It's like, algebraically, I guess that's trivial to solve for alpha, right? You just need to subtract some things to the other side. I guess the only thing that makes it difficult is whether or not you can walk with fractions. So, let's do it. Alpha is now equal to pi minus pi over 2 minus pi over 6. And I guess the detail that I have to go on to from here all depends on how uncomfortable people feel walking with fractions. Should I do the walk to get that into a single fraction, get the common denominators, or should I just wait? Okay. Once one of you has that alpha down as a fraction with pi in the numerator, let me know what you have. What's alpha? I hear a pi over 3. Do I hear a second? Nice. Yeah. So this missing angle alpha is pi over 3. I'm going to put that in the triangle. And there are a few things you can notice now. This triangle is now going to be the triangle we need to study to get all of the trig functions that we still have missing in the unit circle. Because if I want cosine of pi over 6, that's adjacent over hypotenuse. Adjacent is the side length labeled A. Hypotenuse is 1. So if I can figure out the side length A, then I know cosine. Similarly, how about cosine pi over 3? Cosine pi over 3 is also the adjacent side length divided by the hypotenuse. There's the angle pi over 3. What's the side length that is adjacent to pi over 3? Oh, God damn it. There's the angle pi over 3. What's the side length adjacent to pi over 3? I guess it's B. Hypotenuse is still the same? So if I know B, then I know cosine of pi over 3. Similarly, you know all of those things that will happen at the bottom of the page. We just need to figure out A, B, and C. And here's the philosophy that I'll use to get that. I'm going to take that triangle. I'm going to reflect it over the line AC. So there's this line AC. I'm going to do the reflection. So all of these angles are the same as they were above. This angle's pi over 3. This angle's pi over 6. This is a right angle. This side length is B. This side length is 1. I'm going to label this point down here as D. All right. So that was like an arbitrary seeming choice, but it will be useful in just a moment. So look at this big triangle, the triangle ABD. Let's compare the angles in that triangle. The angle here has size pi over 3. Angle down there has size pi over 3. What's the size of this angle? Pi over 3. Because it's 2 pi over 6s. Pi over 6 and another pi over 6 is 1/3 of a pi. So, yeah, I guess if you want to walk in degrees, it's 60 degrees for every corner. Yeah.
Isn't it like 60, 30, 90 triangle?
Yeah, so if you like, I am justifying the side length ratios of the 60, 30, 90 triangle. Because this is exactly that. It's 60 degrees, 30 degrees, 90 degrees. I just have them in radians.
Will it always be those numbers and radians?
What do you mean by always?
Will it always be pi over 6, pi over 2, pi over 3?
I mean, I'll give you other triangles to study. So like on the previous
Well, I mean
page.
for 60, 30, 90.
Oh, yeah. 60 degrees is pi over 3 radians. 30 degrees is pi over 6 radians. 90 degrees is pi over 2 radians. Yeah.
What's 45 degrees? You know?
Mm-hmm. Look at your unit circle. It has some angle conversions on it too. Alternately, you can multiply by pi and divide by 180. So, equilateral triangle, all of the angles are the same. Since it's an equilateral triangle, all of the side lengths are the same. So 1, this side length, will be equal to that side length, 1. That's not exciting yet. Equals 2b. Ooh, so do we know what b is? I guess 1. All the side lengths are the same. One of the side lengths was 2b, another side length was 1. All right. Feel pretty good so far? Nice. So I guess that tells us some things. Cosine of pi over 3 is definitely 1/2. We could probably figure out some other entries in this set of rows now. But instead, let's figure out everything now. So I'm going to redraw the original triangle. So this angle was pi over 6. The hypotenuse had length 1. The opposite side was length 1/2. This angle is pi over 3. There's a right angle. This side length I labeled as A. Do we have enough information that you could determine the side length labeled capital A? Yeah, we also have the Pythagorean theorem, right? A squared plus B squared equals C squared. A squared plus B is 1/2 squared equals C squared. A squared plus B squared equals C squared. That's something you can solve for A. And everyone seems to be doing, so I think I'll pause until someone just tells me what A is equal to. What do we get?
Square root of 3 over 2.
Root 3 over 2. Do I hear a second? Nice. Oh, so that tells us more. Cosine was also just A, is root 3 over 2. Think we could figure out the remaining side? The remaining trig functions right now? So what's the sine of pi over 6? Oh, well, there's something that's just wrong there, right? Ignore that. So sine of pi over 6, sine is opposite over adjacent. There's pi over 6. What's the side length opposite?
1/2.
What's the hypotenuse?
1.
Oh, that simplifies to just 1/2. How about sine of pi over 3?
Square root of 3 over 2.
Now here are root 3 over 2. Opposite is root 3 over 2. Hypotenuse is 1? Yeah. Tangent? Let's talk through tangent a little bit. Tangent will be opposite over adjacent Oh, nice. So it looks like there's the same walk about simplifying a complicated looking fraction again. I guess the first thing I'd want to do is there's a divide by 2 in the numerator and the denominator. So those will undo each other. One over root 3. How does 1 over root 3 simplify? Well, let's see. 1 over root 3, I see a square root in the denominator. I don't like seeing a square root in the denominator. When you see a square root in the denominator, multiply and divide by that square root. That'll get rid of the square root in the denominator and put it in the numerator. So, what should I multiply and divide by? Nice. And what does it simplify to? Nice. How about tangent pi over 3?
Square root of
Just root 3? Nice. All right. I will transfer this over to our unit circle. An angle of pi over 6, also known as 30 degrees, has a cosine value of root 3 over 2, has a sine value of 1/2, has a tangent value of root 3 over 3. A 60-degree angle gives you an x value of 1/2, a y value of root 3 over 2, a tangent value of root 3. Oh, you couldn't see that.
Yeah, that's
But you know what I did, right? I just copied the numbers onto entries in the units. And in fact, the information on this circle now fits a simple enough pattern that I bet you could reconstruct it on your own. The angles that appear on the unit circle are 30 degrees, 45 degrees, 60 degrees, other than the multiples of pi over 2. And the numbers you see in the x, y values are 1/2, root 2 over 2, root 3 over 2. Once you know that much, you know it's going to go everywhere. If the x values go biggest to smallest, the y values go smallest to biggest. So even if you forget your unit circle on your note sheet or something in the future, you can reconstruct this from scratch using that. All right. Any questions before I move on to something else? Cool. So we have these fancy trig functions. Something we like to do with functions an awful lot is graph them. Let's start studying graphs of trig functions. And I bet I can get through this page. All right, so here are two graphs. Multiple choice question. One of those is sine, the other one's cosine. Which one is which? Yeah.
Sine goes to 0.
Yeah, let's check that. So, let's think about 0. You told me sine. What do you mean by sine goes through 0? What is sine of 0? Go through the point 0, 0, because sine of 0 is 0. So whichever one of those is the graph of sine, I'd better go through input equals 0, comma, output equals 0. Which one of those? Oh yeah, so I flipped through forward a couple pages again. 1, 3, 2. Which one of those graphs goes through the point 0, 0? I guess the first one. I meant to label them with A or B. Oh, I did. So it looks like this one should be sine x. Let's check if this other one is reasonable to be cosine of x. What's the cosine of 0? So this graph had better go through x equals 0, y equals 1. Looks like it does. Let's use these entries also. Cosine of pi over 2 is 0. When you rotate forward by a right angle, the x value is 0. So it better go through x equals pi over 2, y equals 0. Pi over 2, 0. Looks good. Sine of pi over 2 is 1. Pi over 2, comma 1. Nice. So now that we have graphs for these things, and maybe the general structure looks reasonable. So what does it look like cosine does? It starts at 1. It goes down until it gets to -1, then it comes back up. Cosine's the x value. There's an angle of 0 radians. It gives you an x value of 0. The angle starts going up. The x value gets a little lower and lower. At pi over 2, the x value is 0. It keeps on going down until you get to an angle of pi radians. Then the x value is 0. Pi radians, the output value is, -1. The angle keeps growing, the x value goes back up, so the x value should start increasing again until it makes it all the way back up to 2 pi, comma 1. So the graphs, I think, look reasonable from the point of view of what the unit circle does. Let's talk about what you can read off of a graph. You can get maxes and mins. By looking at these graphs, so what is the max value that cosine takes? How do you find the maximum value of a function by looking at the graph? highest point. What's the highest value cosine takes? I'm not looking for the x value, I just want the output value right now. 1. Maximum value the cosine takes is 1. X values that produce it. Can you give me an x value by looking at this graph that gives you cosine equals 1 by looking at this graph?
2 pi.
Looks like 2 pi will do it. Are there any other x values that give you that?
Pi.
No, not pi. Pi gives you the opposite. 0 walks though. Any other values?
Negative 2 pi.
Negative 2 pi. Are there any values that you don't see on the graph because it stops too soon? What's another x value that'll give you that maximum? I think 4 pi will do. It'll get you back up to that peak. Maybe also negative 4 pi. And it looks like maybe there's a pattern there. Any even number times pi? How about sine? What's the maximum value sine takes? Same maximum value. What are some x values that give you that maximum?
Pi over 2.
Pi over 2. Give me another. 3 pi over 2. How sure are you of that? That looks like it gives you the minimum again. So, give me another one that negative 3 pi over 2 looks like it does.
Oh, because that does to
Well, also just look at the graph, right?
Yeah.
But yeah, negative 3 pi over 2 is like negative 270 degrees, which is coterminal with 90. If
So
you
5 pi over 2 would have
5 pi over 2 would have been 1, so it would have come back up, make it there. Cool. Yeah.
So for sine, you said that like any positive value times pi would be on the graph. So then for sine, would it be any negative value times pi divided by 2? Something like that?
You mean produces a maximum?
Yeah.
I don't think quite that, because I see pi over 2, 3 pi over 2 was bad, like it gave me a minimum. So I think it's more complicated than that. But we can see something by studying like the gap between those two. What's the gap from pi over 2 to negative 3 pi over 2? What would you get if you subtracted those from each other? So you'd be subtracting a negative, I think you get like 4 pi over 2. So 2 pi. What's the gap from this x value to that x value? Another 2 pi? So I think the pattern is in fact anything that looks like pi over 2 plus pi times something even. Which I guess makes sense because 2, like all the trig functions repeat every 2 pi. All right. We feeling good right now? I think we can get one more line, at least a little bit of the next line. What's the minimum value cosine takes?
negative 1.
Negative 1. Could you read off the inputs that give you that?
Pi. Negative 5.
I think it'll be the odd multiples of pi this time. Sine, the minimum value is negative 1 at x equal 2. Maybe I'll just write it this way. 3 pi over 2 plus anything that looks like 2 pi k, where k is a whole number. And you know what? 2 more laws. Even or odd. Sine boss, does that look even, odd, or neither? Or both? How do you tell if it's even or odd?
Cosine would be even.
I hear cosine is even. So right, if you draw that vertical line, if you were to reflect cosine over the y-axis, do you get the same graph back?
Yes.
Nice. Cosine is even. To check for oddness, you can pin down the origin and rotate by 180 degrees. So I did that, so you don't have to. Does that now look exactly the same as the graph you have in front of you? Oh, so sine is odd. And it looks like I now find myself rather quite a bit behind schedule. We'll see what I do with that. It might mean that the homework posted for today becomes posted for Monday, which would push back its deadline by a week. If I don't do that, then ask me about it on Monday. Ooh, how many people plan on coming to that talk tonight?
I wanted to.
That's a shame.